Hi, we're Team G2T7, and in this presentation, we'll be talking about our image compression algorithm and the various approaches we've explored. In this presentation's overview, we'll begin by discussing Huffman encoding, which serves as the cornerstone of our algorithm. Subsequently, we'll delve into the various approaches we've experimented with, leading up to the unveiling of our ultimate compression algorithm. Huffman encoding allows us to represent individual pixel values or color components within an image with variable length binary codes based on their frequency of occurrence. This results in a compact representation of the image, as the most common values are encoded with fewer bits. In the initial phase of a Huffman encoding process, a priority queue is employed to assign the highest priority to colors with the lowest frequency. This queue serves as a pivotal component of the Huffman encoding algorithm, with its primary role being the allocation of the highest priority to colors with the lowest frequency. This strategic organization of priorities sets the stage for the recursive construction of the Huffman tree. For each iteration, we'll select the two colors with the lowest frequency from the priority queue. Subsequently, we create a parent node that encapsulates these two colors and inserts this parent node back into the priority queue. This iterative process continues until a single root node representing the entire color spectrum has been formed. This strategic arrangement ensures that the colors that occur less frequently in the image are assigned longer bit sequences, while those that are more prevalent receive shorter and more efficient codes. This approach is fundamental to our compression technique, as it optimally captures the statistical distribution of colors in the image. The resulting Huffman tree is structured in a hierarchical manner, where leaf nodes directly correspond to individual colors, while internal nodes are exclusively tasked with storing frequency information. Once we have successfully constructed the Huffman tree, we gain the ability to assign unique Huffman codes to each color present in the image. These Huffman codes are binary representations, typically comprised of ones and zeros. These binary codes play a pivotal role in the compression process. During compression, the ones and zeros guide the traversal of the Huffman tree, enabling us to precisely locate and represent the corresponding color values. It ensures an efficient and lossless compression process, facilitating the faithful reconstruction of the image during the subsequent decoding phase. And to decode it, we simply have to take the code and traverse it in the Huffman tree from the root node to the leaf node, switching to the right or the left branch depending on the ones and zeros in the Huffman code. Each code will allow us to reach a unique character. So for this example, if we have a Huffman code of 1110, for every 1, we'll traverse towards the right child, and for 0, we'll traverse towards the left, and eventually, we will reach the leaf node representing the value 20. Therefore, 1110 is decoded to 20. Now that we are able to represent any set of colors in a tree, let's see how we can get the optimal set of colors. After testing various approaches, including the quad tree, we have ultimately selected two distinct and best performing methods for comparison: octree color quantization and spatial downsampling. Spatial downsampling involves dividing the image matrix into 2x2 pixel blocks. Within each block, we calculate the average RGB values based on the 4 pixels it contains. These blocks are then represented as individual pixels in a new quarter-sized image, with the averaged out RGB values. This process effectively reduces the image size and resolution. When decompressing the image, it will be rescaled to match the dimensions of the original image. Another method that we experimented with is color quantization, where we define a color palette used to represent the entire image. In our experiments, we've tested with different numbers and ended up with palettes of 128 and 256 colors as the best performing option. Color quantization involves color selection with the aid of an octree to find unique and frequently appearing colors. Afterward, we prune the tree to match the palette size by removing less common colors. The result is a color palette that allows us to map each image pixel to the nearest color in the palette. Statistically, spatial downsizing has a significantly lower runtime, as there is no need to construct an octree and a color palette. Notably, the runtime is on average 17 milliseconds, and peak to signal noise ratio is consistently around 20, with MSE on average at 900. In contrast, color quantization is able to give higher quality images in many scenarios, as seen with significantly higher PSNR and lower errors across most images. However, some images, such as image 3 and 8, have much higher loss and error. This is true for both color palettes of size 128 and 256. Comparing the two methods, spatial downsampling has a lower runtime, while color quantization can produce higher quality images on average. However, our team chose spatial downsampling as color quantization exhibits inconsistent performance, occasionally producing degraded images that are unrecognizable after decompression. Therefore, we have decided on spatial downsampling as our main algorithm to focus on. To improve our algorithm, we experimented with different optimizations. We first tried downsampling with 3x3 blocks in an attempt to further improve compression. These are the statistics for the 3x3 approach. It is evident that as we transition from a 2x2 to a 3x3 approach, the images become progressively blurrier. Overall, with a 3x3 approach, the reduction in safe bytes showed a significant improvement of 24% on average. But this, however, was also accompanied by a decrease in quality as indicated in the increase in MSE of approximately 50%, while the runtime remained relatively consistent as anticipated. Upon careful consideration, we have determined that a block size of 2x2 is a more favorable approach as it is a better balance of loss and compression. Our final optimization involves rounding of values. When calculating the average RGB values, the initial values can range from 0 to 255. By rounding these values to the nearest multiple of 10, we can reduce the number of Huffman leaf nodes to just 26. However, this rounding introduces a slight increase in color inaccuracies when representing the image. Here are the updated compression statistics after implementing rounding. Considering the sample image, when comparing the 2x2 approach with and without rounding, there is minimal variance in terms of image quality. Nonetheless, incorporating rounding significantly enhances the compression of the file size. It is evident that the byte savings have improved by 22% on average, which is a significant gain despite the minor increase in errors and slight decrease in PSNR, and therefore, we have included this optimization in our final design. We also experimented using gzip compression, which is part of the standard Java util package, which further improved our compression from 75% on average to 82%. However, we ultimately decided not to implement this as it seemed to provide an unfair advantage and didn't align with our intention to highlight our own hard work and originality. To summarize, our image compression algorithm works as follows. Firstly, we implement spatial downsampling using a block size of 2x2. During this downsampling phase, we calculate the average RGB values within each block. To optimize the data representation, we round these RGB values to the nearest multiple of 10, facilitating more efficient compression. Following the downsampling and rounding process, we proceed to construct a new image that's essentially a quarter the size of the original image. This newly created image uses the rounded RGB values to represent color information, effectively reducing the data size while retaining the core characteristics of the original image. To further enhance compression, we leverage Huffman encoding. By constructing a Huffman tree, we represent the colors in this downsized image efficiently. The Huffman tree ensures that more frequently occurring colors are encoded with shorter bit sequences, reducing the overall data size and facilitating faster transmission or storage. In summary, our approach combines spatial downsampling, rounding of RGB values, and Huffman encoding to produce a compact representation of the original image, while preserving its essential visual attributes. This method allows us to achieve significant data compression with minimal loss of visual quality. And to decompress, we simply have to first extract crucial components from the compressed data. This includes the Huffman tree and the binary data stream. The Huffman tree is essential for decoding the compressed binary data effectively. Once we have obtained these components, we proceed with decoding the binary data by referring to the extracted Huffman tree. This decoding process transforms the compressed data into a quarter-size image representation, which we will then use to enlarge it back to its original dimensions. It's important to note that this enlargement process may result in some loss of image quality due to the initial compression. Despite this quality loss, our approach enables us to reconstruct the original image, ensuring that the dimensions match the original, even though there may be some trade-off in visual fidelity. Our aim was to strike the optimal balance between file size and image quality. After conducting experiments on spatial downsampling, we have determined that a spatial downsampling with 2x2 blocks, accompanied by the rounding up to the nearest 10, provides the ideal equilibrium we were seeking and is our most optimal solution.